Hello everyone. Today we're going to do a couple of second-order circuit examples. I'm Michelle Maharvez.
And I'm Vivek Subramanian. Let's get started. So this is a follow-up to our promise in the last module where we said we would do some examples for you using these second-order circuits. So to do that, we should start with the table we ended with in the last section, which is this one right over here. And this is the list of equations and the calculations associated therewith for the series RLC example that we worked through in the previous module and the parallel RLC module which we did not work through. Now, these are the general form solutions. So this is the total response, which means it includes the possibility of a forced response as well as a natural response. And these are the equations that we get. So you'll recognize these equations from what we had before. So this is the equation, for example, let's take the series RLC. This is the equation for the voltage across the capacitor as a function of time, and you see what A1 and A2 are.
Oh, I see. So what you're saying is if we take the overdamped case, we have the two terms that were the transients we talked about last time, the natural response, and now this is your superposition point. Now there's the forced response.
Exactly.
And then the A1s and A2s depend on some of the initial and final conditions as well.
Now this is an important point. If you look at the general form solution, let's take A1 as an example. If you look at the general form solution to calculate A1, you notice it depends on VC0, but it also depends on VC infinity. And VC infinity is dependent on the forcing function.
Got it.
Right? So A1 and A2 will therefore depend on the forcing function as well in the case where it's not a natural response.
And so the next boxes are the two other cases, critically damped and underdamped.
Correct.
But what's interesting is alpha doesn't depend, nor does omega naught.
Exactly. That's the point. So alpha and omega naught, those calculations do not depend on how we alter our framework. Okay?
Okay.
And you'll notice that the alpha and omega naught values also are the same for the natural response as well as the total response.
Got it.
Right? So what's really changing is the values that go into calculating the coefficients that go into your root calculations.
Okay.
Okay? And so we've got for each of these cases, we have the overdamped, we have the critically damped, and the underdamped. And remember, the overdamped case is a pure falling exponential. The underdamped case, you have an exponential with that oscillating behavior. And the critically damped case was that special case where we kludged it without telling you how we did it, where you have the time dependence in the B2 term. Okay?
Perfect.
And that's the basic idea there. And then over here we have the similar numbers for parallel RLC. So keep these tables in mind, because when we attack real problems, we're going to not rederive these. Rather, you're going to figure out the initial conditions, use those and figure out the overall circuit topology, use those to figure out the respective coefficients, and then generate your result.
Cool.
Okay? Go ahead. Why don't you start, Michelle?
Oh, you want me to do the first example?
Sure.
All right. Example 1. So we're going to start with a series RLC, and it will initially be uncharged.
Okay.
Okay?
So
this capacitor is initially uncharged.
So what I could do is, if I was going to solve this problem, I would recognize that it's a series RLC. I would take that table, and I would immediately pick the left-hand side of that table because that was the series part.
That's exactly right.
Okay.
That's pretty much what we're going to do.
Okay.
Initially, it's open, but you know that the capacitor has no charge, so you know the initial voltage. And then you're going to flip the switch, and it'll force this Vs onto that circuit.
Okay, so this is not a natural response problem. This is a forced response problem.
That's
so we'll
right.
use the total response formulas.
Exactly.
Okay.
And we don't know if it's damped, underdamped. We have no idea yet. So all we know is that this is 16 volts, and we know the values of the three components.
Okay, so let me guess what we do next.
All right.
Since certain parameters don't depend on whether it's forced, underdamped, or not, for example, alpha and omega naught are the same no matter what, it seems like I should start by calculating those.
It seems correct. You're right. Exactly. And before I do that, I just want to point out that the problem does ask us to work out both the voltage across the capacitor and the current through it. So we'll just come back and have to do both.
Okay.
Minor point. Okay. Boom. You're exactly right. Alpha is R over 2L. We know that from the table and from last module's example. Plug in the values and we get 40 nepers per second. And omega naught is 1 over square root of LC. We know that as well. Plug in L and C and we get 25 radians per second.
Okay.
So 40 1 over seconds, 25 1 over seconds. So the question here is, Is this under, over, or critically?
Well, I guess we would have to look at the relationships between those.
Right, so we'd have to compare 40 and 25. So they're not the
right.
same, so we know that's not critically damped. Okay? Is the damping bigger than the resonant frequency? It is,
In terms of the numbers, yes.
Yeah.
Absolutely.
So this is probably, well, not probably, this is probably a damped circuit. This circuit is damped, right? So we're going to choose that form of the equation. And notice it's just like the natural solution, except again we have the forcing function. So the total the time voltage is going to be the final plus these two transients.
Right.
Okay? So now we can do two things. I'll choose one. So I will start by working out the two roots, S1 and S2. But we're also going to have to work out A1 and A2.
Right. Okay, so but it makes sense to start with S1 and S2 because A1 and A2 are calculated from S1 and S2.
That's right.
Okay.
So S1, going back to just what we did in the last module or the table before.
Right.
This is one of the roots, one of the two roots of the quadratic. Put in the values of alpha and omega naught. You see the value of working these out first.
Right. Okay, and I see the point. And this is where you can really tell that, I mean, you can tell obviously directly from the numbers, but this is how you can see that it is clearly a damped situation because this number is going to end up being real.
That's exactly right. You have -8
Yep.
and -71.
Okay, good.
So you know that these things are going to be decaying exponentials. Okay, good. So we've got that part now. And you're exactly right. A1 and A2 are going to be dependent on initial conditions and S's. So let's do the initial conditions first. So I jumped the gun on this one. I was about to ask you, what do you think the final voltage on the capacitor?
I can get it. I can get it. It's 16 volts.
Right. Fantastic. So that and why is that? That's because in the limit, as we've waited a very long time, transients work themselves out, and this capacitor looks like an open. There's no current flowing,
Right.
so this Vs is the voltage.
There's a forcing function in a series circuit of 16 volts, so it's going to settle at 16 volts.
Exactly.
All right.
Okay, what do you think the initial voltage on the capacitor in this
Well, we
is?
kind of know that because we know that there's no charge prior to time is equal to 0, so the voltage should be 0.
Brilliant! And what is the current through the inductor at t equals 0?
Oh, well, that's also fairly straightforward. This is an open circuit, so there's no current flow.
Right.
And since the inductor resists abrupt changes in current, the current at time is equal to 0 will be the same as the current just before the switch closed.
Yep.
So that's going to be equal to 0.
That's right. And we know that the time derivative of the voltage on the cap is
Must
1
therefore
over
also
C.
equal to 0.
Exactly.
Right.
So now we have the initial conditions we wanted, right?
Yep.
Okay, so we've got those down. We've got these. We've got our S's. So it's time to just calculate out the two A1 and A2.
So I just take those equations on the table for A1 and A2 for the damped case of the series RLC circuit.
Exactly.
I plug in the values and I get the values of A1 and A2.
That's right. And
Okay.
that's exactly what you get. You get this A1 is this minus 18.25 and A2 is 2.25. So now we've got the whole thing. It's pretty straightforward to put it together. So I'll just wrap it up and let you do the second example. So here we're just reproducing the circuit. But plugging in all of those numbers from the previous slide, you find that the total response looks something like this. So again, it makes sense. These two transients are going to work themselves out to 0 eventually because they're dying negative exponentials, right? They're dying out.
Yep.
You're going to be left with 16 in the end. That's right, because that's what we know will happen because this is our 16 volt source.
Correct.
And then the time constants of these two things are here. One's bigger than the other, and we have these sort of coefficients. And what we can easily do is plot it, and we get what we'd expect, that this thing essentially decays down. It's overdamped, no oscillations. You see no wiggles.
Right.
And it decays down or up, however you want to think about it, to 16 volts. And that's
So this is kind of interesting. This is an RLC circuit, so the shape of that curve is not the same as an RC circuit that was charging.
That's right.
And because it's really the sum of these two, I mean, you're looking at the effect of two different time constant exponentials.
Exactly. They're both dropping, but they're two different. In fact, if you zoom in, you would have been able to see the hump a little bit.
I see. Okay.
Now, they wanted the current, so let's do that. So we know that the current is I equals C dV dt. Right?
So we just take the derivative of that, right?
Exactly right.
Okay.
And you get this. Now, this one looks a little more interesting because you get something that looks like this. If we were to plot it, you see, it's kind of neat.
So this is the hump you were referring to effectively, because the slope change is going through a maximum, basically.
Exactly. So
Okay.
it's exactly what it is. And so you basically get this slight increased current, and then it drops off. But in either case, it's discharging out.
So there's some sort of hump around here then.
Yeah, that's
Okay,
exactly right.
got
That
it.
comes from these two
Okay.
things. And all it's telling you is the voltage is dropping steadily because the cap is as you know, is adjusting to this force function. But it does it at slightly different rates. That's what the hump means, basically, right?
And that's because of the interaction of the two storage components.
That's exactly what it is. That's why you get this interesting behavior that's more interesting than just an RC.
Got it.
Why don't we do one that's a parallel circuit?
Okay. All right, so let's set up a parallel circuit, and let's go ahead and here's the circuit that I'm going to use. Okay.
Whoa.
And I'll point out some things about the circuit before we start. So at up to time is equal to 0, it's sitting in position 1. Okay, so it's been sitting there forever. So we have a current source driving a parallel circuit that contains what components? When the switch is in position 1, what components are in the circuit, Michelle?
Okay, so R2, L, and C. So, it's not so hard. It's a parallel RLC.
Right, so we would use the right-hand side of that chart.
Got it.
Okay?
All right.
Now, when it switches to time is equal to 2...
Okay. Time is equal to 0.
Sorry, when it switches at time is equal to 0 to position 2...
Got it.
We have this Thevenin voltage source.
But that's weird. It doesn't look like what we've looked at previously.
Yeah, but you're right, because it has a series resistor and then it's driving this parallel combination. But let me give you a hint to help you.
Okay.
So this is a Thevenin voltage source. Can you transform it to anything that will make it look more similar?
Okay, so my guess is somewhere down the line in this example, you're going to get a Norton equivalent
Yes.
for that V0R1.
And then I'll combine that parallel R1 with this R2 to get a straight
And it'll look
parallel
easy.
RLC.
All
Okay?
right, I buy it.
All right. So let's go ahead and get started by first figuring out the initial conditions. And so remember, we're starting at, we're looking at what's happening up to time is equal to 0 minus. Okay, so we want to go ahead and figure those things out. So you agree that this is what our circuit looks like at time is equal to 0 minus. It's been sitting there for an infinite amount of time till this point. So it started at minus infinity, up to time is equal to 0 minus. You know, inductors are shorts, capacitors are open. You agree this is the right circuit?
Yes.
Okay? So let's go ahead then and figure out the various parameters we have. So let's say I know IS. IS is 500 milliamps.
Okay.
Okay, half an amp. What's IL? What do you think?
Well, it's not going through the open circuit, which is the capacitor. And if I have a short in parallel with a resistor, it's all going to go through the short. So,
because of current division.
All the current's going to go through the inductor. So 500 milliamps through the inductor.
Yes, you're right. So IL will be 500 milliamps. Okay? And you see that. And similarly, we can find the voltage across the capacitor. Oh. It's 0. Why is it 0, Michelle?
Because it's an open in parallel with a short.
Exactly.
The voltage across a short is
That's
0.
right. That's right. Okay? And now, because the inductor does not like abrupt changes in current, we also then know IL0 is 500 milliamps, and we know that VC0 is 0 volts. Now, an interesting consequence of that is because VC0 is 0 volts, VL0 will also be 0 volts.
Because they're in parallel.
Because they're in parallel.
Well,
okay?
that's nifty. We got all of our initial conditions.
We have all the initial conditions, and we got it very easily, so that's kind of nice. Okay, now given these initial conditions, the next step is to use that table, specifically the right-hand side of that table, and start figuring out the parameters. So again, this is the circuit that we had, and we need to figure out the parameters. But this is not a pure RLC, right? Because we have in parallel, because we have this R1.
Right.
So to figure out the initial parameters, I first need to do what you mentioned earlier, namely I need to do a Thevenin's to Norton's transformation, a source transformation, and then figure out my effective parallel impedance.
Got it.
So I want to end up with something that looks like this, so that I have a pure parallel RLC circuit.
Oh, I see.
Okay?
So but then that means you're going to have to calculate R prime and I0 prime.
Exactly. I've transformed this, a real voltage source, into this, a real current source. But you know how to do that. That's standard source transformation. And this is that calculation. So I take V0 divided by R. I get I0 prime. I'm just going to call it that because it's a Norton equivalent. And of course now R prime is the parallel combination of R1 and R2.
Yeah.
Okay? And that works out to be 20 ohms. So now I'm ready to proceed because I know my R, L, and C, so I can then calculate my alpha and omega naught.
Oh, I see. So what basically you need to make sure you calculate R prime so you didn't have the wrong component value to put into these. Exactly. And you need I0 prime because that's going to be used for forcing R and infinity.
We're not using it yet, but we are going to use it.
Got it.
Now, let's start with these numbers and look at these numbers. Now, Michelle, you kind of gave the story away early when you said we'll look at a case that is underdamped. But
Yeah, 100 is bigger than 50.
100 is bigger than 50, so this is an underdamped case. Okay, and if it's an underdamped case, in the underdamped formulation, you can also calculate that frequency of oscillation.
Oh, that's right.
Okay?
86
Right, and so we've done that. Now, just as a side, compare omega naught and omega d. So the omega naught is what the freestanding oscillation frequency would be. Omega d is this damped oscillation frequency.
So the damping lowers the frequency.
Yeah, you'll notice the damping has lowered the frequency. Okay, so we're almost ready to go. We have alpha and omega naught. Now we will need those initial, so remember that we're trying to get in the underdamped case, what we have is that sinusoidal formulation, right? So we need to go ahead and set that up. To set up the sinusoidal formulation, we're going to need IL at infinity, okay? And we are going to need to know omega d, which we've got, and we need to know d1 and d2.
Okay.
Okay? Let's take the easy part, IL at infinity. Again, let's review. Let's look at the circuit. Okay, this is the circuit we're looking at. What is IL at infinity? So what happens to the capacitor at time is equal to infinity?
Open circuit.
Open circuit. And the inductor?
Short.
Short. So what is IL at infinity?
It's going to be I0 prime.
Exactly. It's I0 prime. Not I0 because
Right.
we've done the transform. Okay? So IL at infinity is the same 0.2 amps that we calculated over here.
Brilliant.
Okay? Now, we can, given that, we can go ahead and calculate D1 and D2, looking up the equations on the table. And fairly straightforward. D1 and D2, you need all of these terms. You need IL at 0, IL at infinity, VL at 0, alpha, etc. We have everything. We've now got all the parameters that we need.
Got it.
So we just pop out the numbers. We're basically done. And we can then get the overall equation.
Wow.
That's the equation. So you see how these work. Now, these are very specific cases where we did, example 1 was a series case. This is a parallel case, but it's very straightforward. Let's plot it.
So wait, before we plot, let me think about this. So your final value is going to be 0.2 amps. So this
Correct.
thing's got to settle to that.
Yes.
It's got to decay out with an envelope of e to the minus 50.
Correct.
And it's going to
And there's
wiggle.
oscillation.
Yeah, there's going to be some oscillation around 86.6 range per
Right.
second. All
And the oscillation is represented by the periodicity here. Okay?
Let's check
and
it
so
out.
let's look at it. This is the plot.
Uh-huh.
So, asymptotes to 0.2,
Yep.
which is what we expected.
Started at 0.5.
Started at 0.5, which was our initial condition. Has an envelope that decays down and has some oscillation.
Couple of wiggles in there
Yeah,
before it becomes
there's actually several wiggles, but most of them you can't see. They're so small that they're not really visible.
pretty cool.
So that's it. That's how you handle these kinds of problems. So the starting, let's just review how you do it. You take the initial conditions, figure out what the initial values are. From the RL, you try to transform it into a case that you know how to deal with. For example, a parallel RLC or a series RLC.
Mm-hmm.
You then calculate alpha and omega naught. And based on that, you decide whether it is overdamped, critically damped, or underdamped.
Mm-hmm.
Once you've done that, you pick the right general format for
Okay.
the equations. Then you calculate the relevant A's or B's. And
Okay.
you're done.
Pretty
That's it.
All right. We'll see you guys when we see you.
Okay, it's been fun. Enjoy.